Otherwise, coming up next is Bot with We'll Do It Live, Experiments in Self-Modifying Code. Maybe. Oh no. What happened? There we go. Hey everyone. Yeah, my talk is about self-modifying code and what exactly that means and what it looks like in the real world. So a little bit about me. Been into malware for a pretty long time, and I have a variety of other experience as well. So I am professionally, I'm a security engineer, and I have been for a while. I worked for a while on an anonymous privacy preserving system called Freenet. Did some security and routing work for them. Helped create and run this. There's a website called BX Underground. It's a large repository. It's a large repository of malware source code, samples, and papers. It's pretty awesome. I created a publication for VX Underground called Black Mass. It's basically a malware. I think of it as a malware research publication. So third one, hopefully soon. We're waiting on some stuff, but yeah. So what else? Yeah, I've taught classes about rootkit design from everywhere from like userland all the way down to the actual firmware. And then I went to go work for God's favorite idiot for a little while, and then now I sold my soul and I work in the Mongo world. So that's a little bit about me. And what I want to talk to you all about today really is twofold. One, it's kind of my journey into writing code that modifies itself in like an interesting way, and the other is again, like practically, what does this really actually look like? I think a lot of people think about self-modifying code and their imagination kind of goes wild. You see this kind of thing in movies. Now, again, with AI, with that really excellent talk we just had, people, their imagination goes nuts. Oh, the computer's going to go crazy, which is kind of funny because personally, I'm way more worried about people than computers. I think that the AI is not going to take over. I think if anything, it's going to be us in disguise as AI, but that's neither here nor there. So a while ago, about 5 years ago, I set out on a mission basically to create a concept that I had, which was a virus that could kind of basically leverage something that I had been thinking about for a while, which is when we use the word intelligence, in my mind, what intelligence actually amounts to is problem solving ability. And this can come in a variety of ways. When we think about intelligence, we often start with the frame of a human. We think about, okay, well, there's a stick on the ground and I need to pick it up and maybe I need to like hit something. We think about our conditions. We think about how we can only relate to how we process things. But the reality is that we have evolved to process just a limited set of things at a time. I'm only aware of this stage that I'm on right now. There's a limited set of things I can do. Same is true for everyone else. And there's sort of it's become more popular in recent years, but I think a less studied, I'll call it a subfield or interest of AI called swarm intelligence, where effectively you have a collection of programs or objects, sometimes I guess now it's drones, but it could be anything that in and of themselves are not intelligent, but as a group, they reason. Like ants are nature's, prime example of swarm intelligence. So I had never seen any malware that was like this, and I kind of wanted to make a shot at doing that. So I kind of sat down and thought about like, okay, well, what is everything that I would need to do to actually make this, right? And not just like a cool concept, but something that actually works. And then on top of that, I wanted to leverage another widely misunderstood area, which is code evolution. So, thank you. basically there's kind of a subfield. It was really big in the 80s, early 90s, uh, where evolving code or artificial life was taken much more seriously as a topic. There were very popular programs called like Tierra and Core War, and people would enter these contests and effectively create these simple organisms that would learn to thrive in their environment, and they would have them face off against each other, do all these contests. It was really cool. But I wanted to see, I wanted to understand that better. I wanted to understand what the limitations of that were. So I kind of set out and decided I was going to make this. It has been a long time. Yeah, so here we go. So yeah, why would I actually do this, right? Like, am I insane or? So as I mentioned, I wanted to kind of explore the limits of what code evolution actually is. I wanted to make a unique little contribution to the AI space on my own. But there's the bottom point down here I think is also worth talking about. So assuming that all the AI hype is true or becomes true, I'm not necessarily comfortable with the only powers on Earth having access to a super intelligent being that can create things or make decisions or whatever, being like, governments, huge megacorps, and like super, super rich people. I think that is a recipe for a horrible situation. So, thought maybe we can kind of start stepping towards, some kind of safety net that way as well. And obviously for the glory of Satan, of course. Okay, so if we're serious about really doing this, what do we have to design for? So a computer virus really obviously should spread by itself, but it should be small, ideally. It shouldn't have any dependencies because this is how signatures are created. And repetitive code is how signatures are created as well. So it should be small. It should be hard to signature. It should not have obvious dependencies. And I really wanted to, if we're going to have code evolution, we might as well just go all the way and say, hey, like, can we actually combine this together in a network to make it like, manage itself to some extent? I think that's ideal. I think it would be best if there was no single place to attack or take it down, especially if it's like a counter AI. And of course, I've talked for a little bit about code evolution already. But okay, now that we know what our design should be, what kind of constraints are we talking about? So if you talk to a security enthusiast or a person randomly about this topic, a lot of them will immediately start talking about the LLM articles they saw on LinkedIn about like, oh my gosh, it makes polymorphic code and blah, blah, blah. Okay, yes, there's somewhere in some data center, somebody sent a request to an LLM that made a mostly working, kind of sort of working variant of code that was already there. Marginally useful, not really, because, unfortunately, it's not good enough to the point where we'll just build from source and be useful for any code of any complexity. And also, if we're not going to rely on external services, I think people are going to notice like 12 gigs of weights being transferred to the machine. I think they're going to notice like an LLM running on the machine. Who's probably going to notice a little bit. So we have a problem. We have to find a method that actually scales for our solution that isn't terribly noticeable. At least in my mind, what I'm going for is something less noticeable than like some light opportunistic CPU mining of some, pick your currency or whatever. But it should be as or less detectable than that. Okay, so we have some notion of what our final design should be. So the reason I keep bringing up evolution is because actually it turns out that this is quite a scalable approach for machines without taking a whole lot of compute. So the final design looks something like a virus that infects binaries that's passed on from one machine to another, eventually has network communication, forms basically a peer-to-peer network, a small world network, which I will get into what exactly that is and what that means and how that functions later on. Uses a virtual network addressing space to manage, basically do load balancing, manage responsibilities for itself. And then, of course, we'll answer the question of like, hey, can we actually like make code evolve? Is that something we can really do? So before we get too far in, a little history for those who may not know. So viruses today are really not a common thing. Viruses from, again, the 80s until I would say maybe the early 2000s, it used to be that in the wild, there was code that would act much more in line to a biological virus, where it would be essentially a snippet of code or a set of code that upon execution would replicate itself elsewhere to run in other executables without interrupting the flow of the other executables. So so akin to a biological virus. This used to be a really big thing. I actually think it's kind of funny, in the 80s and early 90s, it almost got kind of demo scene-y a little bit. The screens that would pop up when people were infected with something, would get flashier and flashier because people wanted to show off. They should have just done demo scene, but that's okay. But today, this basically, it's very rare. I have seen, recent examples, but it's been quite recent. Mostly viruses are gone, which is kind of sad. So in 2020, I wrote a virus. I picked the Java virtual machine for a few reasons. One, it's everywhere. It's on your SIM card. It's on your phone. It's on Intel chips. It's in your operating system. It's like everywhere. And the other thing is it has a reduced instruction set. It's really not that hard to work with. And it's easy to learn as well. It's nice and simple. So about 5 years ago, I wrote a simple virus for the JVM. It was about as simple as you could get, but it was the first. I mentioned that viruses are fairly rare. It was the first functioning JVM virus since I think it was like 1998 or something. And even the one in 1998. They never even really published the whole thing, so you couldn't even, I assume it worked, but you couldn't recreate it locally or anything. So even just doing this, which honestly, there was some decent work involved, but it was a conceptually relatively simple exercise. It hadn't really been done in like years and years and decades. There were limitations of it. It was kind of successful, but it was brittle. It was just supposed to be a proof of concept. The only things I think I ended up changing on replication were things that I absolutely had to, like the flag that the virus checks to see if a file is infected already, stuff like that. Really, really simple. Effectively, there was no self-modification at all. It just took the code, copied it, and I did get an ego boost a little bit because Bitdefender and Fortinet made a signature for it, which made, it was like, oh, that was really cool. It made me happy. But that also was a sign that like your code sucks. So there's that. So, okay, how exactly does something like this really actually work? So in Java, which again, I would argue is a very simplified version of any actual processor, you have the benefit of knowing always exactly where to go. You don't have to do, finding the entry point is like super easy. You always know like what method is going to run at start. So you have typically, for those who may or may not know, Java applications usually come in zip files masquerading as something else called jar files, which contain a manifest that points to a class that has the actual entry point for the program. So there are a number of things you can do. I kept it really simple, and all this did at the time was take a single instruction to basically start the virus, inject it into the main method, which is always the entry point. And that was kind of that. I mean, it wasn't really, wasn't necessarily magic. So if we break it down a little bit further, what really does the cycle look like? Well, if it's self-contained and you don't have any dependencies, you have to write a parser. Java class file parser, I think the one I wrote is maybe like 150, 200 lines. It's not that bad. And effectively, you have to load the parser into memory. But the trick is you have to read yourself the file that you're in already, identify which methods and code is yours, and then you want to read your target, because you have to. It's obviously not as simple as taking methods and just shoving them into a new binary and suddenly it works, right? There's a lot of adjustment you have to do. So in Java, effectively the equivalent to like a data section in a JVM in a class file is called the constant pool. So you take all of your static data, you take all of your method names, your strings, and all this other stuff. You calculate the new values, the new slots it would have to be in for the constant pool. At that point, after you've changed that in the target and updated your own code to reflect that, all in the same loop, then it really is, at that point, the nice thing about the format is it actually is as easy as just taking the method and putting it directly in the file, as long as you don't have to do anything fancy like initialize an object. So that's why I just made everything static, and it worked. No initialization required, nothing like that. Pretty simple. And then, of course, the final step is to inject an invoke for the start of the virus method at the beginning of main, which is just an invoke static instruction. And that's it. You're all done. So the reason I started with this is because I'm trying to give a realistic idea of, okay, for any form. Oh my gosh, 1 second. Okay. Hello. There we go. Cool. I did this with Java methods, but actually you can do this with any executable format. So PEs, ELFs, it doesn't actually matter. Mako for Mac OS does not matter. You can do it. There are sometimes mitigations like signatures. Obviously, if the hash is different, then something's wrong. Things like that. But actually, this works quite well, and it's not going to change because compiling binaries has never been a simple thing. I doubt it ever will be a simple thing. And so support for this kind of thing needs to basically remain. So this text is really small. Darn, that is not very big. Hold on. 1 moment. Okay, let's try this again. Oh my God. All right, you know what? Take that. Hello? Okay. Yeah, I don't know about that. So how do I use that? Option command 8, and then aha. Thank you, sir. Okay. So just to show a demonstration, this is the file running for the first time. We have our payload class. This is the original infector. You need basically to create a builder. I created basically a builder tool. You specify a payload class. It has a payload. Here, it's some cute text I thought of. But the thing that isn't printed here is the fact that this is searching all local directories for any jars that it has permission to write to. And then down here, I created basically what's called a goat binary, or a sacrificial goat. And up top, you can see when I run it the first time, it's just, a normal application. It does whatever it does. And then after I run the infector, suddenly you can see the first 2 lines are added, but the program continues. So this is kind of what a virus looks like from a practical point of view. Let's see. I'm going to spare the zoom in exercise, but effectively this is one of my favorite reverse engineering tools, and I'm just showing that it's running as infected. It got infected as well. Okay, so that's nice and cute and everything, but where's the self-modification, right? It's nice that, it can modify the constant pool items, the numbers of the constant pool items, and then inject them in. That's not really, you just need that to function. It's not really very special. Well, in the virus world and some malware, there's a concept called polymorphism. Some of you may be familiar with it already. It's not the same polymorphism as in programming, where you define a function several different ways and you can pass one set of parameters or another. It's effectively where upon replication or infection, superficial attributes are rewritten or erased. So method names are rewritten. Variables whose values don't matter are changed, things like that. And I am going to zoom in here. So this is a method that was replicated into Hello Happy Innocent, and as you can see, the original method name was not yo-yo b vd dad 003. So, and then the other thing is, usually in Java applications that people don't protect, the variable names are inserted by the compiler at compile time, and so you can just open it up usually and see, okay, well, they named it cat or dog or hello or whatever they called it. But there's actually no need to put that information in there. So also, some additional changes upon replication. Now we're stripping that information out. We're changing method names, and we're copying everything relevant to that. Okay, so that's nice, and it's helpful to avoid detections. But what would be really cool is if we could actually change the method instructions or like the code flow. That would be really awesome. This is quite hard, actually, because you need to preserve the correctness of the methods that you already have written, but you want to be able to change the program state. So effectively, what we have to do is come up with methods or sets of instructions that we can inject that have no meaning but look really confusing. So I later on wrote an engine to do this that ships with the virus called Samsara. Basically, it creates instructions. It will create instructions that are effectively end up being no ops. So Java's a stack machine. It will put objects on and off the stack randomly. As long as it evens it out at the very end, it doesn't matter. Go-to is an instruction in Java. I didn't know that until I knew it, but you can create random go-to graphs. That's really fun. You can also take a method invocation and basically put it inside of another one. So Java has reflection, so you can actually invoke the method.invoke and then change the string that it's calling. So instead of creating a signature of, oh, this method's being invoked, you can say, actually, this is just a generic invoke method and itself, and it's difficult to create like a signature on something so generic. And then at the very end of the cycle, if the method body is too long, it will try to identify sets of instructions that we know are junk and remove it. So a little bit more about stack manipulation. I kind of just explained this, but essentially we just throw things on, we push things on the stack. Maybe we do some things, and we pop them back off. They never mattered. We also can insert just random calls to methods that either return nothing, simple mathematical operations, stuff like that. Create a new object. It costs nearly nothing to just allocate a new object. And then, of course, let's see, for invocation, yeah, as I mentioned, I literally can just replace the method name inside of method.invoke, and it's hard to create a detection for that. So this was all like, that's all conceptually very simple. In practice, it's like really, really hard. So Java has type safety as a language feature, and it's had this since like 98 or 99. So it's really hard to just take instructions and jam it in there, and the code still runs. Basically, at compile time, the types that are supposed to be available on the stack in local variables, all these things are all tracked. And if you start deviating from any of that, the code will not even run. So this is all tracked with something called a stack map table. And it's kind of exactly what it sounds like. Breaking up on conditional instructions, it will characterize the stack at that time, a stack and locals at that time, and then create the appropriate map. Unfortunately, this is really hard and requires a lot of work. Like, I had to write an emulator. So again, that fits in the virus. So let's see if I can zoom in here. There we go. Yeah, so here I'm, oops, I don't know why that happened. I don't know what the deal is. I'm sorry, I'm not good at Mac. How do I computer? There we go. Yeah, so effectively all the instructions are being processed, and then the object types in the local variables and in the stack on the stack are all being tracked, and from a set of arbitrary instructions, you basically have to recreate the entire stack map. It's really, really hard to get right. So that took like a super long time. So this was all really, really time consuming, and it was not the super sexy AI nonsense that lots of people might be thinking about. Okay, so it's not the most crazy thing ever, but it's functional. It does work. So how can we take it to the next step here? Because I'm quite serious about making the thing that I said I was going to make. So I had this other concept. It was very theoretical at the time, but it turns out it's pretty good. So I had this concept of like, again, a reasoning swarm. So if you suppose you have a peer-to-peer network, and it has a virtual addressing space. And that virtual addressing space, typically in peer-to-peer networks, they correspond to like this file belongs with these computers, or this shard. If you're doing torrenting, this block belongs at this one, and this block belongs over here. And that's great, and that's efficient, and people have been doing that for decades, and it's useful. But what if that virtual addressing space corresponds to other things, like, I don't know, like a problem you're solving? So I wrote about this in Black Mass Volume 1. Oh, by the way, everything I've shown and will show is available online, and anyone who wants to talk to me about it after, I'd love to show you. So, but yeah, and Black Mass is free online, by the way. So it's a PDF, it's free, you can download it. But basically, I started toying with the concept of creating this for real. And so I did some research, and human social networks actually are, one, decentralized. There's often, in a human social network, there's no person that controls everything. Information spreads very quickly. It's very efficient. If people are connected and they want to ask something, it's very common and usually not that long until you get an answer. So it makes sense, actually, that you would take this network topology and see if you can make computers mimic the same kind of thing. And people have been interested in this, somewhat theoretical topic for like decades at this point, but not for nothing, because this guy named Oscar Sandberg in the early 2000s created a paper where basically you can take a virtual addressing space from 0 to 1, and without having like a tracker, without requiring a bunch of new connections or anything, you can change the topology of the network to be effectively what's called a small world network and get efficient search. So let's actually talk about what that means. In a small world network, or like a network that humans naturally form, typically there are a lot of, however you want to measure distance, whether it's geographically or by interest or whatever, it all ends up panning out the same. You have many short distance connections, and then kind of like an inverse log or a decaying exponential of probability that you'll have like a long distance connection. So an example translated into like plain English is, I know many people in LA, I know nobody in China, right? And the reason I know many people in LA is because I live in LA, I talk to people in LA, right? I don't really know anyone in China. And this is how all human social networks end up being. So in Oscar Sandberg's algorithm, we can, inside of what's called a restricted route network, meaning I only need to be connected to like maybe 2 or 3 peers, depending on the size of the network, but a reasonable network could be somewhere between like maybe 3 and 4 peers. And my connection never changes. I don't have to talk to a tracker. I don't have to like ask anybody for anything, which kind of nicely dovetails into the whole viral aspect of it. You can use an algorithm to effectively swap locations. So in this virtual addressing space without actually changing your connections. To do this, the calculation is very simple, but effectively it's you want to ask, are my neighbors, so of the neighbors that I can talk to, is the mean distance conforming to a small world network to my neighbors smaller than my distance to my immediate neighbors? In other words, am I closer to your friends than my friends? And if the answer is yes, you propose a swap, and if it's mutually beneficial, you can calculate it pretty simply. They both swap, and so just by exchanging a piece of information, the actual route of requests changes, and you get this nice efficient search without any like central authority. It's pretty cool. So, I ran it myself. I did it myself. And after running, a simulation of like, I think this is like 1 million yeah, I think it was, I don't remember how many nodes it was, but it was quite a few. I did this really simple comparison. I made them simply change locations in the addressing space, and it converged onto a small world network, which is basically evidence that it will be efficient when we search. And then finally, so like, how do you enforce commands in like a system, or how do you control a system like this? The answer is with cryptographic signatures. So basically, all nodes have their own cryptographic identity, but then the bot master signs messages. So the bot master can connect to any node, issue a command, it can spread throughout the network, and everybody knows it's good because it was signed and timestamped. Okay, so we've laid kind of the foundation. That's all just sort of like the initial stuff. Let's get into the actually cool stuff now. So how do we make code that really evolves, right? Like, how could we create a network where how could we create a network where a bot master can just give a goal and the network will provision and figure things out on its own? I looked at many different approaches, but genetic programming, another old idea, is like really, really efficient. So the basic concepts of evolution are really quite simple. You have randomness, you have genomes, which are effectively sets of symbols that are defined however you like. So a gene could be anything. In many cases, it could be an instruction. You have individuals, so sets of genes. You mutate them, and then based on a fitness function, you select them. And that's all really nice and everything, but there are a few issues with that if we're actually going to start talking about code. So if you just start randomly throwing instructions together, right, like that code's not going to run. Like the odds are super low. It's just not going to happen. You're going to have arguments that go places that don't belong, instructions that don't have the arguments they need or the wrong type. So that's like a huge problem, and has been a main barrier to like this idea being valid. But fortunately for us, back in, it's funny because this has been around for a long time, and I'm actually surprised I don't see people talking about it. But back in about 2010, this guy named Lee Spector had a really simple idea, and it ended up being really, really good. So he created something called PushGP, which is a special kind of computer. Basically, it's a stack machine, but it's not a stack machine in the sense that it only puts things on and off the stack and basically uses that instead of registers. It actually has a stack for every kind of data type, and you can define your own stacks, you can define your own instructions. It's really flexible. And the way you handle bad instructions is simply if the instruction doesn't have the needed items on the stack, simply no op, and this machine will just keep going. It's really like simple. It works super, super well. Okay, all right. So what is actually like a good use case for us to evolve code? I put a lot of thought into this. The key is to keep it simple. So I figured we would simply evolve code that obfuscates other code, or evolve obfuscated code rather. And this is an attempt to be less predictable for things like signatures. So this means we have to use genetic programming, we have to define a fitness function, we have to provide test cases, and we have to provide a set of instructions that we're interested in using. So more specifically, in my case, what I did was I optimized for stack junk, conditionals, and we want it to be long but not too long. Like it should be, it should be decently sized. But if methods start getting huge, then it just becomes really obvious that something's wrong. So this is the part. This is the fun part. All right. So long story short, I implemented that, and a few caveats here. First of all, the thing you're about to see is push GP instructions. So I really wanted to have code that people could like ship by the time my talk happened. You know, best laid plans and all that. Didn't work out. I got pretty close, but don't worry, I'm not going anywhere. But basically, the output of this code is actually in push GP instructions. That happens to still be beneficial to us because we have a push GP VM in our code now. But I would say that if I had more time, what I would have done is simply translate these instructions to JVM instructions, which I will end up doing later. But in any case, check this out. So the short explanation is on all those factors that I mentioned, I basically just created a weighted score. So I think I weighted with different percentages each of the different factors until it basically started looking right. And so now from random code, we can produce code that will actually run and generate obfuscated sets of instructions that produce the same values on the stack at the end as the beginning. That was really fast, and this is a very simple case, but you can see it already runs through 50 generations, but our final program here, so I wanted like 10 and 20. It's just two integer values. It's just a test value. But basically, and then these are push GP instructions. But what we now have basically an evolved set of instructions that even though they do all kinds of different stuff, there's control flow and it's valid and it functions, the end result is still basically no op, right? Like the stack at the end is the same as the stack at the beginning. So I think this is really cool because you can, we basically just generated a method. I think that's really awesome from randomness. Like that's really cool. So the real question is, okay, well, you saw how fast that ran. So like what other problems can we solve, right? And the answer to that question is basically, I didn't have time for it, but however, consider this. All right, so instead of your goal being the same stack at the end as the beginning, what if your goal was the output of a specific method? And if you have a reduced instruction set, you probably will have less errors. And what I'm hinting at here is in the JVM, the most common vulnerability type is deserialization, which is often simply a matter of initializing the correct object in the correct state. So consider this. We have a network with an addressing space that represents whatever we want. We have code that can evolve to the parameters that we want, which is, I'm still actually blown away that it works. I did not believe that it was working at first. It's like actually incredible. But what if we simply map the genomic space, right, to the virtual addressing space, and then we say for every node, you create individuals within this part of the genomic space, like lexicographically, like comparing the genes, say, hey, okay, this node with this addressing space, if it's within this range, only creates genes within this range, right? You can pretty reasonably scale out the network and deeply search the potential genetic space for execution paths, for ways to generate code. So basically, I really wanted to have this all wrapped and integrated into one thing by now. It didn't happen because of how life is, but that's where I'm headed. I'm not stopping. Like I said, I'm not going anywhere. And yeah, that's my talk. I'm just creating a network that can evolve code by itself, and then I would like to make it do vuln research. So yeah, that's my talk. And if anyone wants to talk about this or would like to know more or see more or whatever, this is how to contact me. I also am physically right here, so hey, what's up? But I love Signal and Discord. That's about it these days. I cannot stand social media anymore. I'm sorry. Shout out to Lee Spector for making PushGP. This literally would not have been possible without him. And that's it. So thanks, everyone.